Okay, so today we are into lecture 3. All right. And the content of today is from chapter 2. Okay, this is from chapter 2 of volume 1, Rohan Aviratne. Okay. So in section 2.1 in that book, he talks about vector spaces. And I think all of you learned about this in your engineering mathematics course. Is anyone not taking engineering mathematics? The one taught by Professor Arya Samanta. Please say something because I can't see your chat window now. Anyone who is not taking or has not taken that engineering mathematics course? Okay, I'm not getting any response. There's some
I have
problem?
not, sir, I have not taken the course of engineering mathematics.
Adil, is that Adil?
Yes, sir. Yes, sir.
Okay.
Sir, but
Anybody?
yes, sir. What we had learned in our undergrad and graduation courses, will that suffice us?
Yeah, that will suffice, more than suffice.
Thank you, sir.
So, it is about vector spaces. What is vector space? It's a collection of vectors which need not be just the vector. It could be collection of any objects also, and that they are called vectors in an abstract sense. And it has to have addition and multiplication law. And it is such that if you take two vectors from this space, v1 plus v2, the resultant vector also should lie in the same vector space. So this means we say that it is closed with respect to addition. You add any two vector from the vector space, the result that you get still lies in the same vector space. Similarly, multiplication with respect to scalar, so alpha times v also lies in the same vector space. So we say it is closed with respect to scalar multiplication. Okay, so if a very simple example is vectors in R3. So think of a coordinate system and you have one vector v1, another vector v2. You add these two and the result that you get is also in R3, isn't it? Similarly, you take a vector, let us say, whose column form is 1, 2, 3. You multiply this by 5. What you get is 5, 10, 15. So the resultant vector also is a vector in R3.
Sir, when we are doing addition,
Yes,
the collection of all these resultants of any two vectors, we call it a span. So, is there something similar to in multiplication in scalar or a similar term which which refers to the collection of all these. As
Okay. What is your name, by the way?
Sir Devjit.
Devjit. Okay. So what you are referring to is, let us say you have two vectors v1 and v2, and then when we say alpha times v1 plus beta times v2,
Yes, sir.
so this is called the span, isn't it?
Yes, sir.
Span of v1 and v2.
Yes, sir.
And if you try to think of it geometrically, so you have this v1 and another vector v2, then this span lies in the plane formed by v1 and v2.
Yes, sir.
We can think of a plane containing v1 and v2, and this span is plane formed by v1 and v2. So basically any vector in the plane formed by v1 and v2. Okay. And similarly for multiplication with scalars, when we say alpha times v, so its span is what is called a one-dimensional space, which is any vector in the direction of v itself. That's the span.
A single line.
Single line, yes. Here the span is a two-dimensional plane when you do, addition of two vectors with arbitrary scalars alpha and beta. But with multiplication, what you get is a one-dimensional space, a single line. Okay, so therefore this is also called two-dimensional space, 2D space. Whereas alpha times V is a one-dimensional space. And both of these, this is a vector space in itself. Similarly, this is also a vector space in itself. Can you see why is that so? See, what is the property of a vector space? It is just that it has to be closed with respect to addition and scalar multiplication. That is the only property that a vector space should have. Now, if you think of this span, for example, so you get a plane. You take any vector, any two vector from that plane, you add it, the resultant will still be in the same plane. So that's why it is closed with respect to addition. And then closed with respect to multiplication is also trivial. Take any vector in that plane, multiply with any scalar quantity. What you get is the scaled vector, but in the same plane and in the same direction. So therefore, it is also closed with respect to multiplication. Likewise, if you think of this one-dimensional space, this is also a vector space in itself because you take any two vector in this space. What will be those two vectors? It could be alpha 1v and alpha 2v. You add them, what you get is alpha 1 plus alpha 2v. And this also lies in the same one-dimensional space. Right? So therefore, it is closed with respect to addition, and then it is also closed with respect to scalar multiplication. So these are the two crucial properties that one has to check for a vector space. Also, this 2D space, it's a plane, isn't it? And a plane is a part of the entire three-dimensional space. So we say that this 2D space is a subspace of the entire three-dimensional space. Likewise, this line is a subspace of the entire three-dimensional space. So is the concept of vector space clear to you?
Yes, sir.
Others? Roshan, is it okay with you? See, for more clarity, please read section 2.1. Okay, and I think you will be taught about this in engineering mathematics also. I really haven't done a nice job in telling you about vector space, but please read section 2.1. It talks about vector space, then the dimension of vector space, then there is an inner product in the vector space. There are several things. Please read them. Okay? And it is really simple. It's not hard. You can, in the next class, for example, you can ask me if you have any doubt. Okay? Now let's go to section 2.2. So here we are talking about what is called linear transformation. Now, what is a linear transformation? So it is defined as a function f, okay, a function f which takes a vector, let's say v1 from the vector space and maps it to another vector v2 in the same vector space. Okay, so suppose you have two vectors x and y. Okay, then f of x is equal to y. This is what the meaning of mapping. So this linear transformation maps a vector x to y. So this is just a transformation. All that it does is it takes a vector and maps it to another vector. Can you think of any such physical transformation?
So scaling up or down.
Scaling of a term. Yes, that is also a linear transformation. Very good. Scaling of a vector basically. So scaling of a vector, that's a very good example. It's also a linear transformation. Why? Because here your f of v is equal to alpha times v. So this alpha is then a constant alpha. For any vector v, it just gives you alpha times v. All right? Any other example of a transformation?
Cross product.
Say again?
Cross product.
Cross product, yes, very good. So cross product is also a transformation. But so how now which one is the linear transformation? So we say that f of v is equal to what? When you do cross product, you have to have another vector. So you can have, for example, a cross v. So this a cross thing, that's the linear transformation. Then the question is, what's the property of a linear transformation. You see, as the name suggests, linear, it means that f of alpha times x plus beta times y is simply alpha into f of x plus beta into f of y. So that's the property of linearity. So if the math has to be linear, then it must follow this formula. So if a transformation follows this formula, then we call it a linear transformation. And you can show that the scaling of a vector and this cross product both follow this formula. For example, can we show that this cross product is a linear transformation? So let us try to show it. So f of alpha x plus beta y is then equal to a cross product alpha x plus beta y. But this is also equal to alpha times a cross x plus beta times a cross y, which is also equal to alpha times f of x plus beta times f of y, isn't it? Which is the linearity property. If you're not following, please ask me. If you have any, even a minute doubt, please ask me. No doubt? Roshan, are you following? Roshan?
Yes, sir.
Okay. What about those students who do not have exposure? I'm forgetting their names. One is Saurav, I guess.
Yes.
And
So I am also one of them. So it is okay as of now.
it's okay. Okay, yeah. Then this Niranjana.
Yes, sir, I'm able to follow.
Okay, very good. Excellent. So you see, it's not a big thing. It's like a function which takes one vector and gives you another vector. So this is the definition of linear transformation. And linear meaning it has to obey the linearity rule, which is what I just talked about. All right. Then one of the linear transformation is what's called projection operator. Projection. So what projection does? Think of a plane, for example, a plane having normal n. Okay, and any vector v here, you project it onto the plane, and this is the projection. Maybe we denote by v bar for the projection, or vp, let's say vp for the projection. So can you think of how can I define this projection? So what will be vp? Vp, can we say that it is same as v minus v dot n into n? Can we say this?
Yes, sir.
So you see what we have done is simply removed the component along the normal of the plane. And that's what is done in projection. The normal component vanishes, right? So when you look at any vector from above the plane, all that you will see is just the projection. The normal component will not be seen. So that's the projection. So this is also a linear transformation. So it takes a vector v and projects it onto the plane. Okay, You can also talk of, what is called domain of the transformation and range of the transformation. So for a projection, what is the domain of the transformation? So projection is like a function. So what is its domain? The domain is any vector in the vector space. So that's the entire R3. And what is the range? What is the outcome? That's the range of a function, isn't it? So what's the range? So range is just the plane, right? Because all vectors are getting slammed onto this plane, which is just an R2. Okay? So I hope you got some idea about linear transformation.
Sir,
Yes.
sir, one thing I wanted to ask, like domain and range, like should we say it all vectors in R3 or simply R3 is enough? Similarly, I wanted to ask for range. All vectors in R2 or R2?
Say again, I could not hear you clearly.
Like domain is R3,
Yes.
so should we say R3 or all vectors in R3?
Okay. Yeah, to be more specific, yes, all vectors in R3. Correct. All vector, you are right. All vectors in R3. And range is all vectors in this plane.
Okay.
And what is then the dimension of the domain? So the dimension becomes 3. And what is the dimension of range? It's 2. Do you know how to define dimension? What is the meaning of dimension? Do you guys know?
No, sir.
Okay. So dimension, so for that you have to again go back to a vector space. So it's dimension we talk for a vector space. So what is the dimension of a vector space? That's again discussed in section 2.1. So by dimension we mean the maximum number of vectors which are linearly independent in a vector space. That's the dimension. For example, for vectors in R3, what is the dimension? So its dimension is 3. So you can take a vector along E1, a vector along E2, and a vector along E3. And they are all linearly independent. And how do we define linear independence? So we say that V1, V2 up to Vn, if they are linear combination, which means alpha I, Vi, if this is equal to 0, if and only if all alpha i's are equal to 0, then we say they are linearly independent. So basically, when you sum them with some scalar multiplication, And you can make it equal to 0 only if all the alpha i's are 0. Then we say that it is linearly independent. For example, think of this 1, 0, 0, 0, 1, 0, 0, 0, 1. So these are the three vectors in R3, isn't it? You take alpha 1 here, alpha 2 here, alpha 3 here. Can you make it equal to 0? For any combination of alpha 1, alpha 2, alpha 3, can you make it equal to 0?
No, sir. Unless they are
only 0.
They are all 0, right? So this is equal to 0 if and only if alpha 1 equal to alpha 2 equal to alpha 3 equal to 0. So these three vectors are linearly independent. Now, so definitely the dimension will be at least 3. Let us see, can the dimension be 4? So take any fourth vector, any arbitrary vector. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1, and take a fourth vector, arbitrary. So suppose this is x, y, z, for any arbitrary number x, y, z. And can you make it equal to 0? Then yes, you can make it equal to 0 if you take alpha 1 equal to x, take alpha 2 equal to y, and alpha 3 is equal to z. Well, with a minus sign actually. So you also have to have a minus sign. So alpha 1 equal to minus x, alpha 2 equal to minus y, alpha 3 equal to minus z. And you sum it becomes 0, isn't it? So with four vectors, they are not linearly independent. So the maximum number of vectors which are linearly independent in R3 is 3. And therefore the dimension of R3 is 3. Which also means, so once you have figured out what is the dimension, then it also means that any vector in R3 can be written as linear combination of three independent vectors. Okay, so I hope the dimension is clear to you. Likewise, there is also what is called basis. So what is basis? Basis is those three vectors themselves. The three independent vectors are the basis. So this is a specific example. So if I now come back to this example, this projection thing, or maybe let's go ahead, let's go further top. Yes, sorry, yeah, here. When I said talked of this 2D space, this 2D subspace, which is also a vector space. So what is the dimension of this vector space? Niranjana, what is the dimension?
Hello, am I
Yeah,
audible, sir?
no, now you tell me what is the dimension?
For alpha 1 plus beta 2. This span, right? Span of V1 and V2.
Yes. So this forms a vector space, and what is the dimension of this vector space?
2, right? So 2D space.
Yes, so it is 2. Very good. Why? Because you take three vectors in this space and you can always make it linearly dependent. So three vectors in a plane are always linearly dependent. Similarly, the dimension of this line, that's 1. Okay, so I hope this dimension thing is clear to you, everyone. Okay, and then I was just talking of this projection transformation, and what I said is that the dimension of domain is 3, and the dimension of range, that is 2, because the range is this plane only. So for a linear transformation, you talk of its dimension, you talk of its range, you talk of the dimensions of the domain and range, and there's also what is called null space. Null space for a linear transformation. So what is a null space? So null space of a linear transformation F is such that you take any vector from the null space, it should become 0. So this is the property of null space. Okay, now can you think of what is the null space for this projection operator? Can you guys think about it?
So any vector on the perpendicular n vector line.
And vector perpendicular to it is null.
Yeah, this n, any vector along the
N vector.
normal n. So f of n is equal to 0, and f of alpha n is also equal to 0. Right? Because it's a linear transformation. So all vectors along the normal n, they are in the null space. So what is the dimension of this null space here? So the null space is also a vector space, and the dimension is simply 1. Okay? All right.
Hello, sir. Hello.
Yes. Yes.
Sir, can you please repeat about null space once more?
Yeah. So, okay, let me go back. So null space simply means that when you take the linear transformation, sorry, when you find out the range, or let's say when you apply any vector from the null space to the linear transformation, it should give you 0. So this is the property, you see, that's the property of a null space. If V is in null space, then f of V should become 0. And in this context, for the projection transformation, V is any vector along n.
So that
Just
example was for projection, right? F of
yes,
n. Okay, sir.
this was
Okay, sir. Now I understand. Only for the projection.
yes. You can also show it by applying this formula here. So f of alpha n will be what? This will be alpha times n minus alpha into n dot n into n. Correct? And n dot n is 1, so alpha n minus alpha n, which becomes equal to 0.
Okay, sir. So that's the example for projection, linear transformation.
Yes, exactly. This is
Okay.
only for projection transformation.
Okay, sir.
All right. So we learned about linear transformation, we learned about its domain, we learned about its range, we learned about their dimensions, we also learned about the null space of a linear transformation. Okay? Then there's another very interesting property about whether a linear transformation is symmetric or unsymmetric. And this is simply given by the following law. So if for vectors x and y, f of x dot with y if this is same as x times x dot f of y, then we say f is symmetric. Okay, so that is a definition of symmetry. All right. So here, when I am writing like this, I'm thinking of f as a function. That's why I say f, then inside the bracket, you have the argument x. But from now on, we will simply write this as f into x. Okay, so we are now going to remove that bracket, and it's simply f into x. So this then becomes fx dot y is equal to x dot f of y. If this is satisfied, then it's a symmetric transformation. But in general, a transformation is not symmetric. And for a general transformation f, you can define a transpose. You can define its transpose ft such that f of x dot with y is equal to x dot f transpose into y. Okay, so this is for a general transformation, but if the transformation is symmetric, then f transpose is same as f. And you can relate it to matrices, isn't it? In matrix also similar things happen, isn't it? So indeed, transformations that we just talked about, these linear transformations, they are equivalent to matrices. And I'll also, get there very soon. But I did not want to specifically say matrix. Why? Because matrix is just a representation of linear transformation. A matrix is just the representation of linear transformation. Just like you remember for vectors, the column is the representation of the vector, which changes from coordinate system to the coordinate system. Likewise, the matrix is the representation of a linear transformation, which will change from one coordinate system to the other coordinate system. So I'll just make a remark here. There is an equivalence between matrices and linear transformation. and it is that matrix is the representation of linear transformation. See, till now we just had this abstract function f. We didn't know what exactly it looks like. Just like for vectors, we had the abstract v with an arrow. But when you write it in the column form, then you see what exactly it is looking like. But that column form is particular to a coordinate system. So it changes from one coordinate system to the other. So just like here, so same thing is here. Matrix is the representation of linear transformation. Okay? And this, I'm really talking very briefly. This is discussed in great detail in a linear algebra course. But ours is an elasticity course. It's not a linear algebra course. So I'm not doing full justice to these topics, but just trying to get the gist of what is required for our course. So this brings us to the concept of what is called tensors. We have these linear transformations which are independent of coordinate system, but their representation matrix is dependent on the coordinate system. So I can make that remark here. Matrix changes from one coordinate system to other. Whereas linear transformation remains the same. Again, please ask me if you are not sure about anything. Okay, so having said this, we are now going to introduce tensors. So here you saw, just like vectors, there were linear transformation. In fact, tensor is a more general notation for things which are independent of coordinate system, whereas their representation will change from coordinate system to the other coordinate system. And scalars, for example, are called zeroth order tensors. Vectors, they are called first order tensors. The linear transformation that we just talked about, they are second order tensors. Okay? And finally, the not finally, there are many more actually. Third order, fourth order, and you can keep going. And all of them are independent of coordinate system. But their representation will be dependent on the coordinate system. And we'll also soon see what is the meaning of these orders. Okay? Somebody
Hello.
has any question? Yes?
Yes, sir. So
Yeah.
higher order tensors, third, fourth, and higher order tensors are also linear transformations, right?
Yes, you are right, but they do not take a vector and give you another vector. They
Okay, sir.
take, for example, you are very right. So I was just talking about the linear transformation that we just learned. We just learned here. So he very rightly pointed out that higher order tensors are also linear transformations. But the linear transformation that we learned just now, which takes a vector and gives you another vector, they are second order tensors. There are linear transformations which takes a vector and gives you a second order tensor. There are linear transformations which takes a second order tensor and gives you second order tensors. So the order changes. That's where the orders change. So the ones that we learned, it was taking a vector and giving you a vector. And they are second order tensors.
Sir,
Yes.
does the order of input and output remains the same
When?
always? Like in case of second order tensor, so it will
Yes.
take a vector and give out a
You're
vector.
right. Yes, yes.
So it happens
For
every
third,
time.
for third order tensor, for example, the order is not the same for input and output.
Okay.
Yes. There are two kinds of third order tensors. There could be one which takes a vector and gives you a second order tensor. Or there could be one which takes a second order tensor and gives you a first order tensor.
Okay, sir.
So it all depends on how the transformation is acting on the tensor. But in case of third order tensor, the input and output does not have the same order.
Okay, sir.
Yes. Um, let's talk of a very specific second order tensor, a specific second order tensor. So that is given by the following notation V and this symbol. Let us say V1 and another symbol V2. And this is called Kronecker product. Kronecker product. Or what's called also tensor product. So this is a completely different operation. Till now we learned about dot product of two vectors or cross product of two vectors, but this is what is called tensor product of two vectors. So it's a new operation. Okay, and the output. So it takes two first order vectors, or it takes two vectors, and the output is a second order tensor. Because it is neither a scalar nor a vector, and it's a second order tensor. Okay, so this was a specific second order tensor. Now of course we just wrote it as Kronecker product, but what does this mean? What does it actually mean? So what does this mean? This will be clear when we will know how does this second order tensor or linear transformation acts on any arbitrary vector. To know what a linear transformation is, we have to know how it acts on an arbitrary vector. And in this case, for this particular second order tensor, let us say this is equal to A. Okay, then it acts in the following way: A into X, which is V1 tensor product V2 into X, is defined as V2 dot product X into V1. This is how it is defined. Okay, so this is how it acts on any arbitrary vector. And you could also write this as, because v2 dot x is scalar, you can also write it later on. All right. Are you guys confused? So this is just the definition. It's a definition. So from here to here, when we went, this is a definition. You can't ask why it happened like this. It is just a definition. Are you with me, everyone?
Sir, how it is a second order tensor?
Okay, that is the order is still not clear to us why it is a second order tensor. But yeah, it's a linear transformation. I think that is clear to you, no? Because you
Yes.
see, it took a vector and gave you another vector, so it's a linear transformation.
Yes, sir.
Is it a scalar? So is this a scalar v1 tensor product v2? Do you think it's a scalar? If it were a scalar, see, two vectors can be multiplied to become a scalar only when it's a dot product. It's not a dot product, so it's not a scalar. It's also not a cross product, because after multiplication, it is not giving you a vector. So it's neither a scalar nor a vector. Okay, and why we call it a second order, it will be clear to you very soon. Okay? Yeah.
Sir, in the output, v2 dot x is a scalar, and that
Yeah.
multiplied by v1 will be a vector.
Yes.
So isn't the output a vector?
Output is vector, of course. That's what we learned about linear transformation, no? The linear transformation that we just read. It takes a vector and gives you a vector.
Right, sir.
But I was talking about this thing itself, v1 tensor product v2. Is this a vector? This is not a vector. This multiplied with x is a vector. Isn't it? Okay, so let's proceed further. So this is one particular transformation, and it turns out to be a second order tensor. Now let us think of what could be, how will a arbitrary linear transformation look like? So this is the question now. How does an arbitrary linear transformation look like?
Excuse me, sir.
Yes.
So, sir, I have
Yeah, please go ahead.
till now we have learned that these transformations are like vector or scalars. It is independent of coordinate system,
Correct.
but their representation are not independent of coordinate system.
Correct.
So my question is why we are so what is physically mean? Why we are so worrying about this representation, which is not independent of?
Okay, that's a very good question. Can anyone answer why are we worried about the representation?
Sir, am I allowed, sir?
Yeah, yeah.
Yeah.
Sir, because at the end we have to deal with the theory of elasticity, where we'll be talking about stress and strain transformations.
Hmm.
And ultimately, the physical significance of all these terms comes in those topics when we talk about stress transformation, in the definition of stress itself on a plane. That's why we are talking about these transformations right now. Is it, sir?
No, sir.
Yes,
Actually,
that's
what I
we are
ask
talking about.
is,
But his question is something else. He's asking, why are you worried about their representation? Why
so
not just
it is
forget about
independent of
the
coordinate system.
representation? Why not just forget about the representation and just work with the transformation as it is? Isn't it? That's what you're asking, no?
Yes, sir. So why it is physically? So it is just a mathematical concept, or we have to. So till now it is like looks like it is a mathematical concept. So how we are, means like it is how it is physically going to impact us. So is there any
Okay.
so
Yeah, of course. Before that, I think somebody was saying something. Is it Pulkit?
Yes, sir. I was trying to answer that. We are worried about the representation of the vector of tensor because we need to work in a particular coordinate system. Because if the vector is in another coordinate system, we need to use the tensor in that coordinate system to get the desired tensor.
no how it is physically means impact us.
Okay. So what
I
is your
mean,
name? What's your name?
Rajneesh, sir. Rajneesh.
Rajnish. Okay. Okay. So that's a very good question, and Pulkit answered one of your questions that, but maybe it was not clear to you. I will just restate it, whatever he said.
Sir, maybe
First
because
of all,
all of the things that we'll be working with need to be in the same coordinate system. That is why we are working with the representation.
yeah, I mean also because we have to work with them. See, if somebody, for example, think of vector and its column form. If you don't think of the column form, you will write a vector v as just a v with a arrow. What will it really convey to you? It looks very abstract, isn't it? Just the vector is an abstract thing. But when you start working with it practically, when you practically work with it, when you solve some examples, you will always be in a coordinate system. And then you will have to write that vector in that coordinate system. And that's where the representation comes into picture. Because you finally have to work in a coordinate system. And the same thing goes for linear transformation also. You could have just stayed with linear transformation, but unfortunately not, because you have to finally work in a coordinate system. So you have to know how does that look like? How does that linear transformation look like? Okay. Now coming, the other thing is,
So,
why are
so
why are we learning linear transformation? That's because you will see later on as we proceed through the classes, the linear transform, these will come to you very often. That's why we are learning about linear transformation.
sir, can I add
Okay.
something in the previous point?
Yeah.
Like rotation is also a rotation of a vector is also a linear transformation. So
Yeah.
physically,
Linear transformation.
physically, when we rotate a vector, uh, the rotation will remain same, but the description or representation of that rotation in terms of its components may change due to the coordinate system.
Well, I think you are saying, I understand what you are saying, but others may not have understood it. Others may have gotten confused. What you are trying to say is rotation is a transformation. It acts on a vector and gives you another vector. So it's the same rotation, but when you represent it in a coordinate system, it will have some form. In another coordinate system, it will have another form. I
Yes,
guess
yes.
I would say. Yeah, so yeah, of course. This is what we have been also saying, that because rotation is one specific linear transformation, and for just like for linear transformation, their representation changes from one coordinate system to the other. For rotation also, the same thing is going to happen. And rotation is one such physical example that you are just looking for. And there will be many more such physical examples as we proceed in the lecture.
Sir,
Yes,
sir, one question like for rotation, should we
yeah.
say we have rotated the coordinate system or should we say the vector has changed?
So it depends on what exactly are you doing. So what are you rotating basically? See, it could be that you have a fixed coordinate system and you are only rotating vectors. You are not rotating the basis of the coordinate system. So in that case, the coordinate system does not rotate, but any other vectors are rotating. Or there can be other way around also. You have several vectors in space which are sitting there, but you are just rotating the coordinate system. So you can do both. You can either only rotate the coordinate system, or you can fix the coordinate system but just rotate the vectors. And you can, and the third is that you can rotate everything, coordinate system as well as the vectors which are in the space.
Okay, sir. If we see it in terms of as far as the linear transformation is concerned,
Yes.
scenario what we will say, sir. The vector has changed.
Yeah, so linear transform means it acts on a vector and gives you another vector. So, so it will. So yes, the vector will change. Correct.
Okay, so coordinate system remains the same in case of rotation.
See
Should we
again,
stay
as
like
I. So it all depends on what exactly you are doing. Are you rotating the coordinate system, or you are, see, when I say coordinate system, that means there are three vectors in space, and then there can be many more vectors in the space, and you can represent all those other vectors in space in that particular coordinate system. Okay, so you have the three axes of the coordinate system, and then you have many more vectors also. And then comes the rotation. Now you have to ask, what exactly are you doing? Are you only rotating the coordinate system and keeping all the vectors the same, or you are keeping the coordinate system fixed but only rotating the other vectors? So it depends on what exactly you are doing, and then you have to likewise define the linear transformation.
So usually, is it not that we rotate the coordinate system and then we find the new basis vectors, and then in terms of that we try to define the previous original vector that we had? So is
No,
it also
it's not the usual case. It is not the usual case. Both can be usual case. For example, think of a coordinate system fixed to the ground, okay?
yes, sir.
And think of a vector fixed to a rigid body. Okay, think of a vector which is fixed to a rigid body, and then you throw the rigid body, and the rigid body starts to rotate and translate in the space. So as the rigid body translates and rotates in the space, the vector which is fixed to the rigid body will also translate and rotate, isn't it?
Yes, sir.
So you see, in this physical experiment, the vector fixed to rigid body is rotating, but the coordinate system fixed to the ground is not changing.
Yes, sir.
Okay? If you had also fixed your coordinate system to the rigid body, which can also be done if you fix your coordinate system to the rigid body, and then your vector is also fixed to the rigid body, then both of them are rotating. If your coordinate system is fixed to the rigid body, but the vector that you are observing is fixed to the ground, then the vector is not changing, but the coordinate system is not rotating because the rigid body is rotating. So everything is possible. Okay? So as I told you, linear transformation acts on vectors in vector space and gives you another vector in the same vector space. So it's just a function or a map from one vector to the other. Now this is really an abstract definition, but we have to know how does it look like. So for that, let us try to find out how will it look like. So first of all, how can we uniquely define a linear transformation? So by definition, f takes an arbitrary vector x in the vector space and gives you another vector y. And it's also linear transformation. Now, any arbitrary vector x, how can you represent it if it's belonging to a vector space? Let us suppose I am talking of a vector space in R3. Then x can be represented using E1, E2, E3, isn't it? Are you with me? Any vector in R3 can be represented as a linear combination of E1, E2, E3. Isn't it? Because the
Yes.
dimension of R3 is 3 and E1, E2, E3 act as the basis of this vector space, and any vector you can then represent as a linear combination of E1, E2, E3. So if you can know what is f of E1, what is f of E2, and what is f of E3, then you can know what is f for any arbitrary vector x. What do you think? So any arbitrary vector x, if it is alpha E1 plus beta E2 plus gamma E3, then f of x will simply be alpha times f of E1 plus beta times f of E2 plus gamma times f of E3, isn't it? So what you can see is now, if you just know these three, you can find f for any arbitrary x. So to uniquely identify a linear transformation, all that you have to know is what it is doing to any set of three independent vectors, which could be your E1, E2, E3, or any other set of three independent vectors. So I'll just write that here. To uniquely identify a linear transformation, we just need to know what this linear transformation does to any set of three independent vectors. So they need not be perpendicular to each other. They can be, but it's not necessary. All right? Okay, so So suppose that if I choose those three vectors to be E1, E2, E3, so let us choose them. Let us choose the three vectors to be E1, E2, E3. Okay? And our linear transformation, suppose I write it as A. So A into E1, what is this going to be? It will be some vector which is known to us, because we said now, if we know what it is doing to three vectors, we can know what it is doing to any arbitrary vectors. So suppose A into E1 is equal to some vector V1. Okay. Now can I further write V1 in terms of E1, E2, E3? Let us try to write V1 in terms of E1, E2, E3. So I can say that this is equal to AI1 EI. Can I write this? So this just means that V1 dot EI is equal to AI1. And I have used summation convention here. So A11, A21, and A31 are some constants which tells you that vector V1. What is that vector V1? Is this clear to all of us? You are not saying anything. Saurabh?
Can you explain it once more? Why we had wrote V1 is equals to AI1 EI?
I'm just, see, V1 is some vector. I can always write it in terms of E1, E2, E3. So I just did that. I have just written it in terms of E1, E2, E3. See, V1 will be known to us. So we know what is AE1, we know what is AE2, and we know what is AE3. They are V1, V2, V3. They are three vectors. And we are just trying to write those three vectors in terms of their components along E1, E2, E3.
Okay, sir, I got it. We are basically breaking V1 into the three components.
Yes, exactly. And those three components are A11, A21, and A31. Is that okay? You might think why I'm using it as A11. Why didn't I say it is some alpha 1, alpha 2, alpha 3? You will see very soon why I use this particular notation, AI1. Okay? So, going by that logic, if I say A into EJ for J going from 1 to 3, which is giving you VJ. So, see, with this notation, I wrote all the three equations for J equal to 1 to 3. So J is a free index here, isn't it? And this then becomes equal to Aij EI. What do you think? Is that okay?
Sir.
So it will not have now three components.
Second, it has what?
Sir, it will, if we write it AIJEI,
Yes.
sir, now it will not have three components.
It will not have three components. What does this mean? So for every J, so I goes from 1 to 3. for every j here. So for every j, it has got three components. J equal to 2, you have A12, A22, and A32. Isn't it? Is that okay?
Fine.
Okay. Now I will mysteriously write this A. Let me extend the time also by 10. Can I extend the time by 10 minutes?
Yes, sir.
Yes.
Okay.
Yes, sir.
So extend by 10 minutes. Okay, so it's already done. So we go back. Is it done? Yeah, it is done. Yes. So now I will mysteriously write A as, sorry, Aij I tensor product Ej. And I'll tell you how I could write this. So I'm just saying that this A can be written like this. And to prove it, we should show that indeed A into E1 is equal to V1, A into E2 is equal to V2, and A into E3 is equal to V3. So can we prove it? So let us see. So what is A into EK, for example? See, I can't say A into EI because you already have I and J here. So what is A into EK? It should be VK, right? I have to prove that it is equal to VK. Let us see if that is the case. So this is Aij, EI tensor product EJ into EK. But do you remember from the definition of this specific tensor product here, how does it act on a vector? You have to dot the second one, V2 dot x, and then into V1. So if you use this definition, this is going to become Aij EI of EJ dot product EK, isn't it? From the definition of this tensor product, the way it acts on a vector. And this is now Aij EI into delta JK. Is that correct? Which is again using the Kronecker delta thing. This is now AIK EI. Correct? And what is this finally? Can you see what is this equal to? Look at the definition of this Vj here. Look at this definition of Vj. Vj is Aij EI. So what is AIK EI?
VK.
Vk. And this is what we wanted to prove, isn't it? So what we assumed for A, we have proved that it is indeed fine. So this linear transformation is of this form, A equal to Aij EI tensor product Ej. So A is equal to Aij EI tensor product Ej. So to know a linear transformation, you just have to know these 9 constants. 9 constants are needed. Okay? If you know these 9 constants, you can say that A is equal to Aij, Ei tensor product Ej. Also, you see that these 9 constants actually depend on what basis you have chosen. If by basis I mean this E1, E2, E3 that you chose here in the beginning, the three vectors that you chose to define your linear transformation. If you had chosen it to be something else and then expressed the resulting vector V1 in that something else component, you would have gotten different Aij. Can you see this? So finally, what has turned out that these 9 constants are needed, but they depend on E1, E2, E3. So it is like, if you think of a coordinate system formed by E1, E2, E3. So if you think of a coordinate system formed by E1, E2, E3, then we say then A is said to be represented by the 9 coefficients Aij. And because it has 2 subindex I and j, 2 index, that's why we say it's a second order tensor. Okay, and for third order tensors you will see that it will have 3 indices. For fourth order it will have 4 indices. For fifth order it will have 5 indices. So here, and what does Aij mean? So you can also say that it is said to be represented by the 9 coefficients or by a matrix. That's it. So these second order tensors are denoted by, therefore, a matrix because you require 2 indices. All right. If it were a third order tensor, for third order tensor A, it would be something like this: Aijk, Ei tensor product Ej tensor product Ek. So this is a third order tensor because it has 3 indices. You see here it has 3 indices, and here also the basis, so it has got 3 vectors here. So that's why it's a third order tensor. I hope the order is now clear to you, right? And also it is now clear that all these transformations are actually second order tensors and they can be represented by a matrix in a coordinate system. I hope it is clear to you. You can please ask me some. This is what I will do for today's class. Now it is open to you. Please ask me any question that you have.
Hello.
So here
Yeah.
also,
Yes.
so here also the definition of the tensor product remains the same in the third order tensor.
Definition of tensor product.
Means Ei cross Ej cross Ek. So first we will
Tensor
take one.
product. Yeah, so we don't say cross, it is tensor product. Ei tensor
Ah.
product Ek tensor product Ek.
Okay.
Yeah, so definition of tensor product is the same.
Same.
Yes.
So first we will take one pair like that, and how we will operate it?
Yes, that's a very good question. How do we operate it? So it turns out there are several ways in which you can operate. So let us postpone this discussion for later time. Okay. So there are
Yes.
several ways in which it can be done. But if you just confine yourself to second order tensors, and what we saw is that its representation is a matrix, and that representation will change from coordinate system to other coordinate system. So do you have any question on this? If you have no question, I can do a little more thing, which will perhaps clarify. Just like for a vector, you remember A dot B, the way we did it? We said that you take the transpose of A and then multiply with B. The column form, you take the transpose and then multiply with B, isn't it? For a second order tensor, A tensor product B, when you want to represent it in a coordinate system, let's say E1, E2, E3, then what you have to do is take A but transpose the second one. And can you see what you are getting here? This is A1, A2, A3 into B1, B2, B3. And finally, what you get is a 3 by 3 matrix, A1, B1, A1, B2, A1, B3, and likewise. Right? Also, look from here itself. What is A tensor product B? You could write it as A EI tensor product BJEJ, which is equal to AIBJ into EI tensor product EJ. So this is your AIJ. So AIJ is equal to AIBJ. What does this mean? What is A12? That is A1B2. And look at this here, A12. First row, second column. This is indeed A1B2, isn't it? Likewise, you can prove for all the components here. So bottom line, for tensor product, when you want to represent it, so tensor product of two vectors you want to represent, take the column form of the two vectors and transpose the second one and then multiply. For a dot product, you have to transpose the first one, but for tensor product, you have to transpose the second one. Then only you can get a matrix. Okay, I hope this is clear to you also. So we have 2 more minutes, so you can ask me, otherwise the time will lapse.
Sir, tensor product and outer product both are same only?
Both are same, yes, both are same.
Okay, sir.
Sir, is dyadic product the same as tensor
That is
product?
also the same. Very good. Dyadic product is also the same thing. So I'll just write here, tensor product. You can ask more questions, but I write. Yeah?
Sir, why we were so much curious about knowing whether the vectors are linearly independent or dependent?
Why we are so curious? You mean here for finding out the representation of linear transformation? I'll have to extend my time. I can extend it if you have no problem. Let me extend it, but if you want to go, you can leave. Yes, so I have just extended it. Now your question, why are we curious? As far as here, while finding the representation of a transformation is concerned, you see, if you had not taken three linearly independent vectors, you had just taken three vectors which were not linearly independent, then you could not have spanned the entire vector space with those three vectors. And just by knowing what that linear transformation does to those three linearly dependent vectors, you could not have found out what is the linear transformation doing to all the vectors in the vector space, right? To find out what is the transformation doing to all the vectors in the vector space, you have to choose three linearly independent vectors. Isn't it? Then only you could do what I just wrote above. Let me go up there. You see this thing here? This I could write for any arbitrary x in the vector space only if your E1, E2, E3 were all linearly independent. अगर वो linearly independent नहीं रहता तो x को हम लोग सभी x को E1, E2, E3 से represent नहीं कर पाते, है ना? मान लो कि E1, E2, E3 ऐसा लिया कि एक ही प्लेन में है वो, तो फिर सारा x थोड़ी ना आएगा उससे सिर्फ वही x आएगा जो उस प्लेन में है, तो उससे पूरा f के बारे में पूरा कहां से पता चलेगा फिर? Okay, any more question?
Sir, is changing. Hello, sir.
Yeah. Yes, Roshan. Hello.
Hello, sir.
हाँ बोलो बोलो.
Sir, if we change the basis of any coordinate system, then it is a linear transformation or not, sir?
फिर से बोलो. If I change the basis of the
coordinate yes, sir. Any coordinate system, then it's a linear transformation, sir.
Then it's a linear transformation.
That means, sir, that means, sir, if we change the basis of any coordinate system and we write the vector, that means the vector only the representation changes. Then we say, hello, sir.
हाँ बोलो या बोलो.
Sir, then we say it's a linear transformation because you say, sir, in linear transformation it is independent of coordinate system. So suppose
Yes.
if we change the coordinate system, that means if we change the basis E1, E2, E3 to another E1 prime, E2 prime, and E3 prime, another basis. Then its representation, that is column form, changes.
किसका column form? Linear transformation का?
No sir. कोई वेक्टर का सर, किस any वेक्टर.
वेक्टर का चेंज हो जाएगा. Yes. फिर
तो सर क्या हम उनसे लीनियर ट्रांसफॉर्मेशन बोल सकते हैं?
जो ये तो सिंपली वेक्टर का कॉलम फॉर्म चेंज होना हुआ. वेक्टर तो अभी भी वही है, उसी वेक्टर का.
यस सर, वेक्टर तो वही है.
नए कोऑर्डिनेट सिस्टम में लिख रहे हो तो यहाँ तो कोई लीनियर ट्रांसफॉर्मेशन लगा ही नहीं है.
यस सर,
कोऑर्डिनेट सिस्टम में लिख रहे हो.
यस सर. सर तो चेंज बेसिस को चेंज करना एंड रोटेशन वेक्टर आर बोथ डिफरेंट थिंग्स. यस सर.
हाँ, यस इट इज डिफरेंट. देखो यहाँ पर अगर वेक्टर्स वही रह जाता है तो जस्ट सोचो इसका मतलब क्या है. लीनियर ट्रांसफॉर्मेशन जो है जिस वेक्टर को लेता है उसको वही बना दे रहा है. सो इट इज आल्सो कॉल्ड आइडेंटिटी ट्रांसफॉर्मेशन. आइडेंटिटी ट्रांसफॉर्मेशन जिसका कि मैट्रिक्स फॉर्म जो आइडेंटिटी मैट्रिक्स होता है.
yes,
तो उस ट्रांसफॉर्मेशन आइडेंटिटी ट्रांसफॉर्मेशन बोलते हैं जिसमें कि वेक्टर वही रह जाता है. तो यहाँ पर अब हम लोग जो है थोड़ा सा बता पा रहे हैं कि देखो यहाँ पर जैसे रोशन ने बोला कि कोऑर्डिनेट सिस्टम तो चेंज कर दिया है लेकिन वेक्टर सारा वहीं पर है. जो वेक्टर पहले जहां था वो वहीं पर अभी है. तो इस केस में लीनियर ट्रांसफॉर्मेशन जो होगा वो आइडेंटिटी होगा क्योंकि वेक्टर्स को तो चेंज हुआ ही नहीं. वेक्टर्स A into V is still V, क्योंकि
Yes,
वेक्टर्स
sir.
आर सेम। तो कोऑर्डिनेट सिस्टम के बेसिस चेंज करने से, सिर्फ बेसिस चेंज करने से, और अगर वेक्टर सारा वहीं पर है, तो उसमें जो लीनियर ट्रांसफॉर्मेशन है वो आइडेंटिटी है।
Okay, sir.
सर
हाँ,
सर जब बेसिस चेंज करते हैं तो वो मतलब उसको ऐसे बोल देंगे कि सिर्फ बेसिस चेंज हुई है, या ऐसे बोल देंगे कि कोऑर्डिनेट सिस्टम चेंज हो?
वेल दोनों कर सकते हैं। कोऑर्डिनेट सिस्टम चेंज हुआ इसका मतलब है कि बेसिस चेंज हुआ होगा। समटाइम्स कोऑर्डिनेट सिस्टम को जो है ओरिजिन भी होता है उसमें, तो बेसिस टुगेदर विथ ओरिजिन इज योर कोऑर्डिनेट सिस्टम। तो कोऑर्डिनेट सिस्टम को हम लोग ट्रांसलेट भी करते हैं। जब ट्रांसलेट करते हैं तो बेसिस वेक्टर तो चेंज नहीं हुआ, लेकिन उसका ओरिजिन चेंज हो गया। तो इस सेंस में थोड़ा डिफरेंस है दोनों में।
ओके सर।
हाँ
Yeah, hello, sir.
हाँ
Yeah, so I have a confusion still that key. Suppose we are in a vector space and we are looking at a deformation, and
yes
so by changing the coordinate, or you said that the representation will change. So are we
yeah
really going to see that the force which is doing the deformation will change, or is it something that is observer is feeling something that is going to change?
या
So
इट इज जस्ट समथिंग दैट द ऑब्जर्वर इज फीलिंग। देखो फोर्स तो एक वेक्टर है, तो कोऑर्डिनेट सिस्टम के चेंज करने से वेक्टर चेंज नहीं होता है, बस उसका रिप्रेजेंटेशन चेंज होता है। तो सो जो फोर्स जो भी लग रहा है बॉडी में वो तो वही फोर्स है, बट कोई अगर उसको
yes, sir.
मेजर कर रहा हो किसी कोऑर्डिनेट सिस्टम के रिस्पेक्ट में, तो अगर कोऑर्डिनेट सिस्टम चेंज कर देंगे तो वो अलग अलग मेजर करेगा उसको, बट वेक्टर वही है वो।
Yes, sir. That's where my confusion is. So
हाँ
vector will be independent of coordinate system, but their representation will change. So
यस
my question, so is the whole thing that we are studying is about the observer, the observer? So
Yeah, I mean, when you solve it on computer, for example, किसी भी मैकेनिक्स प्रॉब्लम को जब कंप्यूटर में सॉल्व करना होगा, तो हम लोग वो वेक्टर को बस वेक्टर वी नहीं लिखेंगे, हमें वहां पे उसका कॉलम लिखना पड़ेगा, वहां पे उसका
yes, sir.
3 कॉम्पोनेंट को लिखना पड़ेगा। तो दैट्स व्हाई रिप्रेजेंटेशन इज इम्पोर्टेंट, क्योंकि कंप्यूटर में जब भी कोड करेंगे तो उसका 3 नंबर्स डालना पड़ेगा वहां पे, और वो नंबर किस कोऑर्डिनेट सिस्टम में है फिर वो इम्पोर्टेंट हो जाता है।
Okay, so there is no physically it is going to change. It is just a mathematical
ये
thing.
या
Okay, okay, sir.
Okay, so I think we had a lot of questions today. So can we end the session today?